So this is Unlock Circuits 18EC42, Module 1, Lecture 3, Part 2. We had discussed in the Part 1 small signal operations and models. And so we'll be discussing now the voltage gain. In the last class, we had discussed about the small signal operation model, collector current and transconductance, then the transconductance geographical interpretation, and then the base current and input resistance at the base, and emitter current and input resistance at the emitter. Now we'll take up the voltage gain. So when we talk about voltage gain, it is the output by the input voltage. Output voltage is the voltage which is taken out at the collector. Now because we have emitter grounded, therefore we say that output voltage is VCE itself. Now we should remember that we are talking about, whenever we talk about gain, we should consider only the AC signal. We should consider only the AC signal which is across this. But VCE, we should remember, is the instantaneous value which will contain both the DC value as well as the AC value. Similarly, when we talk about the voltage gain, it is the output by the input. Input, when we talk again, it is VBE. VBE is this value, AC voltage of the VBE we should consider when we talk about voltage gain, right? Not the total, instantaneous value here. The instantaneous value is VBE, which is DC plus the, this is DC is because of the biasing, and this is because of the input signal which is to be amplified. So it is, if you really see here, the value of the gain is small VCE by small VBE. So both are AC signals here. Gain is always with respect to AC signals, right? So how do we derive this is what we will be considering now. So the total collector current voltage, this total, whenever we say total, it just means the AC plus DC are the instantaneous value. VCE is equal to, this VCE is equal to this value of VCC minus the current flowing through the resistance multiplied by the resistance itself. Okay, this minus the voltage across this. Voltage across this is this current multiplied by the resistance here. So VCE is equal to VCC minus ICRC. That means we are just writing the loop equation for this. We are just writing the loop equation for this. There are many different ways of writing this. We can write, VCC is equal to ICRC plus VCE, or you can write VCE is equal to VCC minus ICRC. Any way which you feel, you can just try to write it. Okay, VCC is equal to ICRC plus VCE, or VCE will be equal to VCC minus ICRC. Both you can try to write that, right? Say if I try to annotate over here, I can write over here as VCC is equal to IC, the I value capital here, C, IC, RC plus the V. You can't write with this very properly. VCE, C capital, E capital, right? So now if you want to find this VCE, then naturally it will be VCC minus this, and that is what is written over here. Okay, so now the value of IC, which is the instantaneous value of the collector current, will be again DC plus the input current due to the input signal. Sorry, the so to say AC current. IC is nothing but the DC value of the collector current and AC value of the collector current. Okay, both together. So you can separate it out. You can just merge it with this. That is ICRC. You are merging with this, and the small IC into RC is written over here. Now this value is the DC value of, this is DC, this is DC, totally it is DC, and that is VCE. Okay, VCE minus ICRC. So out of this total thing, this value is the DC and this value is the AC, and this is nothing but the small VC. So small VC is minus ICRC. So this is DC bias voltage, and this is the signal voltage, which is VCEs. Okay, output signal voltage due to the input signal voltage VBE is VCE. So signal voltage, as I said, VCE is equal to minus ICRC, and that is written over here, and that will be minus GM VBE into RC. Okay, minus GM VBE into RC. That is because the value of IC we already found it to be, I think it is better to clean. Okay, so we were just trying to see what is the value of the IC. The IC value we have already found to be equal to, I think it was there earlier. Okay, IC is equal to GM into VBE, right? So this is what we need to write there. Same thing we are just replacing, right? So we are writing in place of this IC GM VBE with a minus sign as it is, and RC over here, and hence we will get, you know, what you call this value. We are just trying to take this out. So VCE by VBE will be equal to the value which is minus GM into RC. AV is equal to VCE by VBE, that is minus GM into RC. You can write for GM the value minus IC by VT, which again we have derived in the last class, right? So where was that? Yes, transconductance value, GM is equal to IC by VT. That is substituted there, and we can try to write that. But the standard one is just this, minus GMRC. To remember, you can always write that as minus GMRC. Okay, so from this we can say that GM is directly proportional to the, you know, collector, bias current IC, and the gain AV will be stable as the collector bias current is, made. Okay, so because of the sol value, IC is a constant value, AV is proportional to the GM value over here. Okay, now we need to separate this signal and the DC quantity, and that is generally done by the capacitor, which is written or connected here and here in the amplifier, and these two capacitors connected here and here are known as the uh, coupling capacitor, which we are not showing in these figures. Okay, we are not showing the coupling capacitors, but they'll always be there. So the large signal equivalent circuit will contain the total current DC plus AC, all this total current and total voltage, and here also total voltage, total input voltage, total input current, total output current, and total output voltage. So all total are instantaneous. You can call it as total or you can call it as instantaneous, which will contain both the DC as well as the AC, DC as well as the AC. Now, if you remove the AC signal, then it is only the biasing which will be there. Okay, when we talk about the biasing, then naturally this AC signal is not there, and you are left with VBE is only DC, and it becomes again the biasing value IB, IC, VC. All these are capitals. You can see that all these are capitals. Here, the V and I are capitals, but C and B, if you see there, C, B, and this BE and this CE all are for instantaneous value or total value, the suffixes will be capital, but letter will be small. Both suffix and the, you know, mm, value of the current and all that will be capital when we talk about bias. Whereas when we talk about the small signal over here, all of them will be the what you call small letters. So here, when we come to this, we are just removing this VB from over here and connecting only the small VB over here, right? Small VB. So at that time, we'll have small IB, small IC, small IE, and all these we have found. We have already found this relationship. IB is equal to VB by RP, IC is equal to GM, VB, IE is equal to VB by RE. All these expressions we have already found in the last class. So this becomes the small signal representation. Please remember that when we are trying to write this, both this DC as well as this DC are shorted, and both are DC voltages. DC voltages are shorted when we want to do the analysis, and if there are current sources, DC current sources, they'll have to be open circuited. And here in this circuit, we don't have that. But in case we have the DC current source, then that should be open circuited. That's what is mentioned over here. Small signal representation of a BGT is done by eliminating the DC sources. Since the voltage of the ideal DC voltage source does not change, we see that the voltage of the ideal DC voltage source will not change. Therefore, the signal voltage across it will be 0. Okay. Whenever we write the, what you call biasing circuit, we'll have to write the DC voltage. Whenever we write the small signal circuit, DC voltage source should be made equal to 0. So VCC and VBE should be shorted. This is shorted, this is shorted, then we'll get this figure. Since the current of the ideal DC current source does not change, the signal current through it will be 0. Signal current through it will be 0. That is, the current source is open circuited. We don't have current source here. That's why this point does not arise over here. Whereas this arises because we have two voltage sources, VBE and VCC, which are DC, and both will be shorted, right? So the resulting circuit is the equivalent circuit of the transistor as far as the small signal operation is concerned. So thus we get a equivalent small signal model. But however, now this transistor has to be replaced by the, its own model. This transistor has to be replaced by its own model, which might be hybrid pi, RT, or whatever we do now. So now we replace that by a hybrid pi model, right? Hybrid pi model is just here, R pi, and this is GMVBE. The base 2 emitter junction is replaced by R pi, and base 2 collector junction is replaced by GMVBE. And that's again straight away from, here, the current here is, IB is equal to VB R pi. VB is the voltage given here. IB is the current which is flowing here. Therefore, this part of it is replaced by R pi, which is VBE by IB. Okay, VBE by IB. That's what we have here, right? Equally well, if we see there, here we have IC GM VBE. IC is equal to GM VBE. And this is the, the current value, and hence we have the corresponding current source GMVB over here. GMVB over here. Now you can see that the, you have input as voltage, output as current. Okay, input as the voltage across R pi, and the output as the collector current. Therefore, we call this as a voltage controlled current source. Voltage controlled will be corresponding to the input side. Current source is corresponding to the output side. Okay, voltage controlled current source, or it is also known as, when the output is the current and input is the voltage, then that becomes a transconductance amplifier. It becomes a transconductance amplifier. Now, Coming to this over here, what we are doing is we are just replacing this GMVBE by means of beta IB. IC can also be written as beta IB. IC can also be written as beta IB. So now what we are telling is we are considering, rather than considering the voltage here VB, we can consider it as IC and IB. So when we consider the IC and IB, then the current amplification will be IC by IB. Here the transconductance will be IC by VBE. So then we'll call it as current controlled current source. Current controlled current source. So current controlled means input side is current. Current source means output also is a current. So this is considered as a current amplifier where we can write the value as, IC by IB. IC by IB is the current amplification. So for that, we'll try to write this, what you call expressions. This we already derived. IC is equal to GMVB, IB is equal to VB into R pi in the earlier class, right? We just need to look at them. Here we already have this, all these expressions we already have, you know. So nothing to, IC is equal to GMVB is already there. And what do we want? IB is equal to VB by R pi. In the derivation of the R pi, we might have mentioned that. So this is R pi and this is VB by IB. So IB will be VB by R pi. So there are different ways of just representing the same thing. And now the value of IE is the combination of both IC and IB. IB flowing here, IC flowing here, both will join and they'll become IE. Emitter current is equal to collector current plus the base current. That is the standard formula. Emitter current is equal to collector current plus the base current. And IC plus IB will be, this plus this. That's what is written there. VB by R pi plus GM into VB. So VB by R pi is taken out common, then this will become 1 plus GM R pi. 1 plus GM R pi. And GM R pi is nothing but the value beta, right? And we can take this, numerator to the as denominator of the denominator. So then it will become VB divided by R pi by 1 plus beta. And this R pi by 1 plus beta, again, we have derived it as RE in the last class. Okay. So you can see this equation over here. R pi is equal to beta plus 1 RE. So RE will be equal to R pi by beta plus 1. So we can just replace that as VB by RE. So IE is equal to VB by RE. Okay. Similarly, we can try to write here IC is equal to GMVB and VB will be equal to the IB R pi. VB is equal to IB R pi, which is IB current here and R pi over here. That is equal to VB. And we can write GM R pi together over here and it will become IB. This is nothing but beta. IC is equal to beta IB. Or IC by IB will be equal to the beta, that is the current gain, AC current gain. So hybrid pi model, whatever we are using here, is the most widely used model, but sometimes we do use the T model, which otherwise is not there in the syllabus, but really speaking, it is very important. So the model parameters GM and R pi depend on the values of the DC bias current IC. So we know GM is equal to IC by VT and R pi will be equal to beta by GM. Beta by GM is R pi. GM is equal to IC by VT and R pi is equal to beta by GM. So which we have already found in the last class, right? So this is there, beta by GM is R pi, and the other one also we might have found. GM is equal to IC by VT. This is the standard formula which we should remember. GM is equal to IC by VT, and the value which is, R pi is equal to beta by GM. These two formulas we should remember. So having done that, then we can just see the T model. So this is the T model over here. In the T model, what we are doing, just compare this with this. If you transfer this resistor to this side, if you transfer this resistor to this side, the voltage you see here is VBE. Okay, we want the voltage here as VB. If I transfer here to this, current flowing through that will be IE. Because the current flowing through that is IE, the resistance here will become RE. It will no more be R pi. Okay, the reason is because of the reason that IE is equal to VB into RE. VB divided by RE. So IE is equal to VBE by RE. What does that mean? VBE will be equal to IE RE. If IE is equal to VBE by RE, then VBE will be equal to IE RE. Here VBE shows IB into R pi. Here VBE shows IE into RE. Okay, both are same. VB is equal to IB R pi is equal to IERE. Okay, so if I transfer the resistor from here to here, the value of the resistance becomes RE because of the reason that here the current is IB and here the current is IE. And similarly here also same thing. If I transfer the resistance here from here to here, then the value of this resistance will become RE because of the reason that here the current is IB and here the current is IE. Okay, and that is all is mentioned over here. Okay, if you transfer that resistance from the base side to the emitter side, okay, where R pi becomes RE, we'll get from the pi model the T model. That's all, nothing big about it. Okay, so now this will be a voltage current or voltage controlled current source, and this will be a current controlled current source. So again, we can try to derive the relationship, that is, IB plus IC will be equal to IE. IB plus IC. This IB flows here, IC flows here, both will get added, and then that will become IE. So IB he is writing here as the value which is nothing but, okay, IB. So IC plus IB is equal to IE means IB will be equal to IE minus IC. IE is nothing but the voltage VBE divided by RE, and that's what we have written here, minus the IC which is GM and that is what is written here. So again, VBE by RE you can take common, 1 minus GMRE you'll get, and this value of GMRE is nothing but alpha, okay, and alpha is equal to beta by beta plus 1. Again, this is the standard formula. Alpha is equal to beta by beta plus 1. Okay, I don't know whether you studied it in devices, but however, this formulas you should remember. Alpha is equal to beta by beta plus 1. Okay, and beta is equal to alpha by 1 minus alpha. Beta is equal to alpha by 1 minus alpha, or alpha is equal to beta by beta plus 1. So RBE, the value of, if you simplify this and try to write it, then you will get in the denominator itself the value beta plus 1, and this is nothing but R pi, which we have already derived, and that's why we are writing like this. IB is equal to VB by R pi. Similarly here we have IC is equal to GMVB, VB is IERE, and you can join them together, and IC will be equal to alpha into IE. IC will be equal to alpha into IE. So RE is the input resistance. In terms of, if you write the RE, RE, then you will get it as alpha. IC is equal to alpha into IE. So we have here a systematic process to analyze the, transistor amplifier. First, what we do, determine the DC operating point, and that determine the DC point means find out the DC collector current. First, we need to find the DC collector current. Then calculate GM, RPi, and RE using whatever formulas. IC by VT, standard is beta by GM or VT by IB, either of them, but beta by GM is the most commonly used. RE is alpha by GM or VT by IE. Okay, they use these formulas to find GM, RPi, and RE. Eliminate the DC sources by replacing each DC source with a short circuit and the DC current source with an open circuit. Then replace the BJT with the small signal equivalent circuit model, either pi or T, generally pi, okay, but sometimes T is also used. Analyze the resulting circuit to determine the required quantities, voltage gain and input resistance. So first determine IC, find GM, RPi, RE, eliminate the DC sources, replace the BJT with the circuit model, then analyze the total resulting circuit for voltage gain and input resistance. That is the process which we should follow. Okay, so if you have any doubts, you can ask. Maybe you can put it in the chat. I'll just, stop